Timing is everything. Without timing, there is no control, no synchronization, and no reliable system. Today, we solve this problem using electronics, oscillators, and software. But ancient engineers had none of that. No electricity, no code, no sensors, and no displays. Yet they still managed to build clocks that worked with impressive precision. In this video, I'm going to break down how ancient clocks actually worked, not from a historical point of view, but from an engineering perspective by analyzing the mechanisms, the control logic, and the physical principles behind them. Measuring time is not about numbers or clocks on a wall. From an engineering perspective, it is about creating a stable and repeatable process. You need motion that behaves predictably, does not accelerate uncontrollably, and can be divided into equal intervals. Today, we achieve this using crystal oscillators and digital timers. Ancient engineers had to achieve the same result using only physical systems. Their entire challenge was to take continuous natural motion and transform it into consistent, controlled cycles. That is the real foundation of timekeeping. Every machine needs energy, and ancient clocks were no exception. Ancient engineers relied entirely on natural energy sources. The sun was used as a reference through Earth's rotation. Water was used as a continuous source of motion. Gravity was used through falling weights. Each of these sources introduced instability. Water flow changes with pressure, gravity causes acceleration, and sunlight is not always available. Ancient clockmakers understood these limitations and designed mechanisms specifically to compensate for them. This is exactly the same design mindset used in modern engineering when working with unstable power sources. Energy alone does not create accuracy. Regulation is what makes precision possible. Ancient engineers developed mechanical regulation systems that acted like motor control loops. In water clocks, the flow rate was controlled using carefully designed openings and container shapes. Floats were used to adjust motion automatically as water levels changed. In weight-driven clocks, resistance mechanisms slowed down acceleration. These systems did not rely on calculations or software. The regulation was embedded directly into the physical design of the mechanisms itself. The most important breakthrough in mechanical timekeeping is the escapement mechanism. Without it, a mechanical clock cannot function accurately. The escapement takes continuous motion and releases it in controlled equal steps. Each step represents a fixed unit of time. From an engineering point of view, the escapement behaves like a hardware clock signal. Continuous energy goes in and discrete timing pulses come out. This is the mechanical equivalent of a digital timing reference, achieved purely through geometry, friction, and inertia. Gears in ancient clocks were not just used to transmit motion, they were used to calculate by selecting specific gear ratios. Engineers could precisely control speed, direction, and timing. Tooth counts represented mathematical relationships. The Antikythera mechanism is the strongest proof of this concept. It used a complex shear system to model astronomical cycles and predict celestial events. This device functions as an analog computer, where physical movement replaces software instructions. The computation happens continuously without electricity or memory. No mechanical system remains perfect over time. Friction increases, materials wear out, and environmental conditions change. Ancient clocks addressed these problems using mechanical feedback. Floats adjusted water flow automatically. Counterweights balanced uneven forces. Periodic recalibration corrected accumulated error. These are early forms of feedback systems. The machine responds to its own state and corrects itself through physical interaction. This is the same principle used today in robotics, automation, and control systems. Ancient clocks show that precision does not depend on advanced technology. It depends on understanding physical behavior and designing systems that work within constraints. These mechanisms demonstrate core engineering principles that are still relevant today: energy management, control, feedback, and timing. When we reverse engineer ancient clocks, we are not studying obsolete machines, we are studying the foundation of modern engineering thinking. Conclude, ancient clocks show us that precision does not come from technology alone, but from understanding physical principles and designing systems intelligently. By reverse engineering these mechanisms, we see how motion, energy control, and feedback were combined to solve the problem of time measurement long before modern tools existed. This way of thinking is still essential today in engineering, robotics, and system design. If you found this analysis useful, feel free to like the video, share it with others interested in engineering, and subscribe for more content focused on understanding how things really work. Thank you for watching and see you in the next video. Bye.